Hello everyone, and welcome back to the AI Research Roundup. I'm your host Alex. Today is May 6th, 2025. Alright, so we're looking at an interesting ICLR conference paper titled Learning to Discretize Denoising Diffusion ODEs, published just over 3 months ago, back in January. This paper tackles the slow sampling speed of diffusion probabilistic models, or DPMs. They introduce LD3 to learn better time steps for the underlying ODE solver, reducing costly neural function evaluations. Okay, so moving on. The authors provide Table 1 early on to position LD3 against existing approaches like Watson et al., AYS, and others. They compare them on key criteria defined in the caption: training speed, noting LD3 is fast, stability, adaptability to the solver and network, and whether they directly optimize the global truncation error. Well, this really helps set the stage for LD3's advantages. Okay, so Figure 1 visually breaks down the LD3 approach. Panel A depicts the initial idea, trying to make the student solver exactly follow the teacher solver's path. But Panel B shows the crucial tweak, the quote, soft teacher forcing objective. This lets the student aim for a slightly different starting point nearby. Panel C illustrates how this relaxation actually leads to better learned time steps, making optimization easier. Alright, building on that visual explanation, these tables detail the actual performance numbers. We're looking at FID scores. Remember, lower is better on latent diffusion models for LSUN and ImageNet, and also stable diffusion results. Notice how LD3 consistently achieves lower FID scores compared to other methods, particularly in those really low NFE regimes like 4 or 5 steps. Well, it really shows the benefit of those learned time steps for quality. Okay, so this Table 2 on page 8 provides more specific FID comparisons. We see results on CIFAR10, AFHQV2, and FFHQ using 2 different solvers, Uni_PC and IPNDM. LD3 is compared directly against other discretization methods, like GITS and DMN across different NFEs. Well, notice how LD3 consistently gets the lowest FID, particularly at NFE equals 4. For instance, on CIFAR10 with IPNDM, it drops FID from 35 down to 9.3. This really backs up the earlier claims. Okay, so following up on that CIFAR10 result with the IPNDM solver, this table compares LD3 not against other learned methods, but against common heuristic time step selections, like time log, SNR, or time uniform. Well, LD3 consistently achieves the best FID scores across all NFEs shown. Look at NFE equals 4 again. LD3 gets 9.31, while the best heuristic is nearly 30. It really highlights the benefit of learning the discretization. Okay, so diving deeper, this Table 7 presents an ablation study on CIFAR10 and FFHQ using the DPM_solver++. It essentially breaks down LD3 to see which parts are most important. Well, notice how the full setting consistently gets the best FID scores compared to versions using hard teacher forcing with L_hard or simpler L2 loss. This really validates the effectiveness of that soft teacher forcing objective we discussed earlier. Okay, so after seeing the importance of soft teacher forcing in the ablation, this Figure 6 provides another perspective. It plots the root mean squared difference, or RMSD, which measures the global truncation error against the number of function evaluations. Well, LD3 consistently shows the lowest error compared to DMN, GITS, and the baseline across all NFEs shown. This directly demonstrates LD3 is better at minimizing that error, which was the core objective. Okay, so wrapping up, we saw LD3 directly minimizes that global error. The key takeaway is that LD3 offers an efficient way to accelerate diffusion sampling, achieving impressive quality, especially in low NFE regimes, thanks to learned steps and soft teacher forcing. And it's remarkably fast to train. Alright, That's all for this segment of the AI Research Roundup. Thanks for joining me. I'm Alex.